everyone, welcome to our today's lesson. And today we have been given a beam that is overhanging beyond the support B. It is supported on three supports: support B, support C, as well as support D, and the beam is fixed at its end E. The whole beam is loaded with a uniformly distributed load, but we still have an additional point load on the member C to D, and we are expected to plot the bending moment diagram for this beam using the moment distribution method. So ladies and gentlemen, join me so that we see how we usually plot the bending moment diagram for such a beam step by step. And if you are here and you haven't yet subscribed to this channel, please hit that subscription button and we are going to appreciate. Now we are going to begin with the calculation of the fixed end moments. That is always the beginning of analyzing such a beam. So we have the fixed end moments, and we are going to begin with the span AB. And in this case, the span AB is an overhanging member, and therefore the bending moment at B, that is MB, will be given by negative WL1 multiplied by L1 over 2. And in this case, W is W1, that is the UDL between A and B. And this is going to give us W, which is 2 kilonewtons per meter, multiplied by the span, which is 2 meters, multiplied by half of that span. And that is going to give us a bending moment at B of negative 4 kilonewtons meter. We go to the span BC. The span BC is loaded with a UDL of 3 kilonewtons per meter, and its span is 5 meters. Now we are going to determine the fixed end moment at the support B, and in this case the fixed end moment here is going to be an anti-clockwise moment, and therefore is going to be given by this formula: negative W2 L2 squared divide this by 12, whereby W2 is the UDL, 3 kilonewtons per meter, L2 is the span B to C. This is going to be equal to negative W, which is 3, multiplied by the span 5 meters. Therefore, that's going to be 5 squared. Then we divide this by 12. And when we do so, we are going to get a fixed end moment at B being equal to negative 6.25 kilonewtons meter. So that is the fixed end moment at B. Then we go to the fixed end moment at C, which will be given by positive W2 L2 squared divide this by 12, and this will be equivalent to positive 3, which is the UDL, multiplied by the span B to C, that is 5, then divide this by 12. And when we do so, we are going to get the fixed end moment at C being equal to positive 6.25 kilonewtons meter. We go to the span C to D, and in span CD, we need the fixed end moment at C. So the fixed end moment at C will be given by the span C to D is loaded with two types of loads. We have a UDL of 3 kilonewtons per meter. We also have a point load of 8 kilonewtons, and therefore the fixed end moment at C will be given by negative. Now, due to the UDL, we are going to have W3 L3 squared divide this by 12, whereby W3 is the UDL and L3 is the span C to D. So we have A to B being L1, B to C L2, C to D L3, D to E L4, and so on and so forth. Then we add, due to the point rod, we are going to have W multiplied by AB squared, divide this by L3 squared. So that is due to the point rod at F, which is 8 kilonewtons. So that will be our overall formula for the fixed end moment at C. Therefore, this will be given by negative W3 is 3 kilonewtons per meter, L3 is 5 meters, then that is squared, we divide that by 12. Then we add W, that is the point rod of 8 kilonewtons, multiplied by A. A is the span C to F, which is 2.5, so that is 2.5, multiplied by B, which is 2.5 as well. We square it, and then we divide this by L3, which is 5, and then we square it. When we do so, we are going to get a fixed end moment at C being equal to 11.25. So the fixed end moment at C will be equivalent to negative 11.25 kilonewtons meter. Then we go to the fixed end moment at D. This negative is because the fixed end moment at C is going to be anti-clockwise. So for anti-clockwise, we got negative bending moment. For clockwise moment, we got positive fixed end moment. And therefore, the fixed end moment at D will be given by positive W3 L3 squared, divide this by 12 because of the UDL between C and D, plus due to the point rod we are going to have W A squared B, divide this by L3 squared. And as we said earlier, you are supposed to take care here. When we are determining the fixed end moment at C, we are squaring B. When we are determining the fixed end moment at D, we are squaring A. So this is going to lead us to positive W3, 3 kilonewtons per meter, L3, 5, so that is 5 squared, divide this by 12. Then we add W, the point rod, 8 kilonewtons per meter, A, 2.5 squared, B, 2.5, divide this by L3 squared, which is 5 squared. And when we do so, we are going to get positive 11.25 kilonewtons meter. So that is the fixed end moment at D. So we are done with the span C to D. Now, after we are done with the span C to D, we are going to go to the span D to E, and therefore in span D to E, the fixed end moment at D, that is FD, will be given by negative W4 L4 squared, divide this by 12. Divide by 12. And this is going to give us negative W4, 3 kilonewtons per meter, that is the UDL. The span is 5 meters, that is the span D to E. Therefore, 5 squared, then we divide that by 12. And when we do so, we are going to get a fixed end moment at D. Fixed end moment of negative 6.25. So we got negative 6.25 kilonewtons meter. Then we go to the fixed end moment at E. It is going to be clockwise. This negative is because the fixed end moment there is anti-clockwise. So at E, the fixed end moment is going to be clockwise, and therefore positive W4 L4 squared, divide this by 12, which will be positive W, 3 kilonewtons per meter, L4, that is 5 squared, and then we divide that by 12. And when we do so, we are going to get a fixed end moment at E of positive 6.25 kilonewtons meter. Awesome! So we are done with all the spans, and we now got all the fixed end moments. Now, after we are done with the determination of all the fixed end moments for all the members of this beam, the next thing we are going to determine are the stiffness factors as well as the distribution factors for all the members on this beam. And we are going to begin with distribution factors for the members BA and BC. And we are going to have distribution factor for member BA is going to be 0. That is, distribution factor for the overhanging end is usually 0, and the distribution factor for the member BC is going to be 1. So anytime we got an overhanging beam, the distribution factor on the overhanging end or the overhanging member is usually 0, and the other member is usually 1. Then after that, we move to distribution, or this we move to stiffness factors for members. Stiffness factors for members CB and CD. Members CB and CD. The stiffness factor for member CB will be given by 3EI divided by the member CB, that is span L2. Now, 3EI over L2, because the beam is overhanging beyond B, and therefore that's the formula that we are going to have. And it's going to give us 3EI over L2, which is 5 meters. Then we go to stiffness factor for the member C to D, and the stiffness factor for CD will be given by 4EI divided by L3. Reason being, the beam is continuous at D, so that is the formula for calculating the stiffness factor, and this will be 4EI divided by L3, which is 5 meters. Then we need the total stiffness factor, summation of stiffness factor. This is going to be KCB plus KCD, and this will be 3EI divided by 5 plus 4EI divided by 5 as well. And that's going to give us a summation of a stiffness factor, that is summation of K being equal to 7EI divided by 5. So that's what we got. Now, after calculating the stiffness factors for member CB and CD, the next thing we are going to determine are the distribution factor for member CB will be given by stiffness factor for member CB divided by the summation of the stiffness factors, and this is going to be 3EI, that is the stiffness factor for member CB, which we got it here, divided by 5, and then we divide this by a summation of K, which is 7EI divided by 5. And we are going to have this distribution factor for member CB will now be equal to 3EI over 5 times reciprocal of this will be 5 divided by 7EI. And when we do so, we are going to get a distribution factor of 3 over 7. So that is a distribution factor for member CB. Then from there we go to distribution factor for member CD. It will be given by stiffness factor for member CD divided by the summation of the stiffness factors. And this is going to lead us to KCD is 4EI over 5. So we got 4EI divided by 5. Then we divide this by summation of K, which is 7EI divided by 5. And when we do so, we are going to get a distribution factor for the member C to D being equal to 4EI divided by 5 multiplied by reciprocal of this summation of K, that is 5 over 7EI. And this will give us a distribution factor of 4 divided by 7. So that is it. Then from there, we move to our next members. Stiffness factors for members DC and DE. For DC and DE. DC and DE. Very good. Now, we are going to have the following. The stiffness factor for member DC will be given by 4EI divided by DC. We got the span L3. The reason being, the beam is continuous at C, so that is the formula. And this will be 4EI divided by L3, which is 5 meters. Then from there you go to stiffness factor for the member DE. The stiffness factor for the member DE. Stiffness factor, let me use the symbol K. So KDE, and for this one, stiffness factor KDC. Good. That's now perfect. So the stiffness factor for the member DE will be given by 4EI divided by L4. 4EI because the beam is fixed at E. So when a beam is fixed, that is the formula of determining the stiffness factor. And this will also be equivalent to 4EI divided by 5. Very good. Then the summation of the stiffness factor for those two members will be 4EI divided by 5 plus 4EI divided by 5, which will be equivalent to 8EI divided by 5. Very good. Then, after determining the stiffness factors for those two members, the next thing will be determination of distribution factors for members DC and DE. DC and DE. And we are going to have the following. Distribution factor for member DC will be given by stiffness factor for member DC divided by the summation of stiffness factors for those two members. And this is going to be equal to 4EI divided by 5 all over summation of K, that is 8EI divided by 5. And this is going to give us 4EI divided by 5 times reciprocal of this, that's going to be 5 divided by 8EI, and that's going to give us a distribution factor for member DC, distribution factor of 1 over 2, that is a half. Then we go to distribution factor for member DE, and that will be given by stiffness factor for member DE divided by the summation of stiffness factors, which will also be equal to 4EI over 5 divided by summation of stiffness factors, that is 8EI divide this by 5. And when we do so, we are going to have this 4ei all over 5 times reciprocal of this, that is 5 divided by 8ei. And when we do that, we are going to get distribution factor for member DE being equal to 1 over 2. So, ladies and gentlemen, we now got everything that we need for us to now fill our distribution table. So, join me in our next episode.